Hi, welcome to Lecture 1 in the electronics series of videos. In this series, we're going to get you geared up so that you can do everything you need to do to make some really advanced projects with Arduino. But first, you have to do some really basic stuff. In this video, we're going to go over Ohm's law, which for our purposes will be how to protect your circuits using a resistor. In order to use Ohm's law, we're going to need three vocabulary words: current, resistance, and voltage. You already know that metal is full of all these electrons that can move around fairly easily compared to other materials. That's why they're conductors. The flow of those electrons is called the electrical current. It's measured in amperes or amps, and it's abbreviated A. 1 amp is a lot of current, just for context. Resistance limits the flow of current. It's measured in ohms. This can vary from anything from a number less than 1 into the millions and millions of ohms. And voltage is what pushes on the current. It's measured in volts. A battery like we'll use in these videos, it might be 3 volts, or it might be something like 9 volts. Arduinos will push with 5 volts. Ohm's law can be written out in a couple of different ways. We have an equation, so we can do some algebra to it to write it however we want it. But probably the most useful way to memorize it is the way I have it written out on this slide, which is that current is voltage divided by resistance. Since voltage is on top here, as you increase the voltage or you increase the push on the current, you're going to have more current. And since resistance is on the bottom, if you increase the resistance, you'll have less current. And this may seem reminiscent of Newton's second law, which is that acceleration is force divided by mass. Right? The more push you have, the more acceleration you have. But the more mass you have, the less acceleration you have. Here's our first example. We'll go through a couple of these examples, and then we'll get into stuff that just really specifically applies to things that you're going to do. So this example is a toaster plugged into 110 volts, and it realistically draws about 4.5 amps of current. So how much resistance did the people designing it put in so that it would work? Here you can see what I'm doing is I'm just writing out Ohm's law, that current is voltage divided by resistance, and then some algebra happens, right? And then I'm solving for resistance. And when I plug in my numbers there, 110 volts divided by 4.5 amps, I get that the resistance necessary to make that toaster work was 24.4 ohms. And that's pretty low, right? That's pretty low. And you might notice that a toaster has low resistance and gets really hot and is dangerous. Right? More safe things are going to have much higher resistances. Here's another example. You know, the incandescent light bulbs. I don't even own one to show you an example of. But they had the bulb, and inside they had the filament that just heats up, and they get really hot. And if you touched one, you might burn yourself. They would draw a current of around 0.5 amp, which is a lot, again, from a 110 volt outlet. So how much resistance was made to be inside of that light bulb? And really that's all those light bulbs were. It was just you had the one electrical lead, you had another, and then you had a coil of wire that was just a resistor between them. And it would just get so hot that it glowed. And here I've written out Ohm's law. I'm solving it for resistance. And then I'm just plugging in my numbers, 110 volts divided by 0.5 amps. And there you can see we're getting about 220 ohms. Okay. And that, it may seem safer than a toaster oven, but you still wouldn't touch any of this stuff, and it's so hot that it would burn you. The next thing we'll need to talk about is the difference between series and parallel circuits. If you were to go and look into a physics textbook, you might see some really advanced theoretical looking stuff for circuits. We actually don't need to use a lot of the theoretical stuff to do some advanced circuitry. Instead, we need to have a good understanding of the basic ideas. For example, a series circuit you can think of as all the components, they're all just in a row. Okay, everything is just in a line. And what I've done there is I've written out plus 5 volts. It goes through 2 resistors. Those squiggly lines are resistors. And then it goes to ground. So I've written out G and D for ground. And you can also see the lines getting smaller as they go down. That's the symbol for ground. Those 2 resistors are in series. And so the electricity will flow from the 5 volt outlet through resistor 1, through resistor 2, and then to ground. And that acts like a complete circuit. The important things to note about a series circuit is that the resistances add. So if you need to add 50 ohms to that circuit, you take a 50 ohm resistor and you just plug it right in. Okay, if you need to add 200, you just take a 200 ohm resistor and put it right in. And the current, if you have 0.5 amps going through one resistor, you have 0.5 amps going through the second resistor as well. And then, as we'll see later, the voltage drops across components, but don't worry about that yet. In parallel circuits, you'll notice that the plus 5 volt pin has a wire coming out of it that then splits into 2, and then each of those 2 wires goes through one resistor, and then each wire goes to ground. The difference here is that the electricity, the current, has a choice of which resistor to go through. And this is how you can tell very easily a parallel circuit from a series circuit. If there's a choice, it's parallel. Now, the big thing to remember about a parallel circuit is that going into that junction where it says plus 5 volts, and then it hits that dot where then it splits into the 2 wires, each of those 2 wires receives 5 volts of voltage. So there's 5 volts pushing across each of those resistors. Right? Then the current can go whichever way it'll go based on the relative resistances, which we won't worry about for now. What we do want to do is protect our LEDs. Now, most LEDs can withstand around 0.02 amps or 20 milliamps. Now, they're supposed to have 0 resistance where if they're off, if you're below a certain voltage, they're off and they have infinity resistance. If you're above a certain voltage, they're on and the resistance goes to 0. They don't really work like that, but we can treat them like they do to some extent. Now, the important thing about an LED is that even though they don't have very much resistance when they're on, they will cause the voltage to just drop by a certain amount. And I don't expect you to understand what I mean without working through some examples first. Here's an example of protecting an LED. That LED that we burnt out, it could withstand about 0.02 amps of current. And when the electricity passed through it, it started out at 9 volts, but it dropped 1.8 volts as it passed through. And so coming out the other end was about 7.2 volts. What that means is that when we use Ohm's law, we can treat that 1.8 volts that the LED is sort of, it's taking it away. We can treat it like it was never there in the battery to begin with. And so what we'll do here is on that top line where it says resistance, the necessary resistance is voltage divided by current. Instead of the applied voltage, what we can actually do is subtract away the voltage drop from the LED. And so we have 9 minus 1.8. We'll divide that by the 0.02 amps that are allowed to pass through, and we can see that we need a resistor of at least 360 ohms. If I had put in a 360 ohm resistor in that circuit, it would have lit up just as brightly, it would have been perfect, and it wouldn't have burnt out. It would have lasted, probably for days, actually. But what do you do when you have 2 LEDs in series, which you will do? In this case, you're going to have to take your 9 volt battery, or whatever the voltage is, minus 1.8, minus 1.8, and that's the voltage you're actually applying. Then you can divide that by the current allowed through that LED. And in this case, if I had 2 of those LEDs that I burnt out, I would need to protect that circuit with a 270 ohm resistor. And I want to take just a quick moment to say, where did that 1.8 volts come from? Or how did I know that the voltage drop on that LED was 1.8 volts? I just looked it up on the bag, right? That's it. There's no big secret. They're all between 1.5 and 4 for the really high power ones. That's it, right? I just looked them up on the bag. And if it's red, you can guess 1.8. If you want to protect two LEDs in parallel, let's say you want to make something like a string of lights that's going to go along the top of one of your projects and have a bunch of light coming down. You're going to need several LEDs, and you'll want to wire them in parallel. And you'll notice that in this diagram I have your 5-volt power supply, which then splits, and one wire, so 5 volts goes through a resistor and the LED, and 5 volts goes through the other resistor and the other LED. So each of these branches sees 5 volts going into it, and then thankfully we can just forget about the fact that it's a parallel circuit and treat them as independent series circuits. And that's actually not too bad, right? Because then we just apply Ohm's law, we solve for the resistance we need, we put that resistor value there, and then we move on. Now, in your pack of resistors, here's a pack that I keep on my desk, right? And you can see it has, let's see if it'll focus, lots of different values of resistances there. Now, I see a 330, I see a 470, and a 220. I don't see the values that I calculated before. But what you can do is you can take the nearest value. If you have too low of a resistance, if you take the nearest value down, you do risk damaging your LEDs. As long as you're close, you're probably okay for these types of projects that we'll do, but in general, you'll want to do the next value up, even if it means it's not quite as bright as it would have been otherwise.